Okay, in this video, I'll be going over the final exam study guide. So, yeah, let's start. So for number one, it's, what's it called? It's the Born-Haber cycle. So with those, you always start off with a formation equation of NaCl, since that's what we're working with. So NaCl, a formation equation, like, it's just a chemical reaction, like, of the two things that make up this compound. So sodium and chlorine. So it'd be solid sodium and chlorine gas. But you see here, there's two chlorines in this side, but only one here. We can't put a number 2 right here, since a formation equation is just for 1 mole of sodium chloride. Which means we put a half mole here instead. Since half of 2 is just 1. See, 1, 1. Okay, so with that, we're gonna make our little graph for the Born-Haber cycle. So here's just, I guess, energy. You don't really gotta label these axes, but I like to. Okay, so first you start off by putting these a little above the, what's it called, the base right here, like somewhere right here, make straighter, right there. So solid sodium and your half mole of chlorine gas, like that. And here you bring it down right here. This is gonna be your heat of formation, which is given to you. It's negative 411 kilojoules. And here is going to be your final product. So just NaCl. Okay, so you want to work up towards that, you know. You guys should be comfortable with like the Born-Haber cycle at this point. And if not, you should look at your past exams since since that was covered in past exams. Okay. Anyways, let's start off by basically just following the steps as shown in the study guide, because on the exam you'll also be given the steps like in order. So first it's the heat of sublimation for sodium, which is 109 kilojoules. So that makes sodium here a gas, and we just bring up the chlorine, which is unaffected so far. Okay. And then so now we're dissociating the chlorine. So and that energy right there is 243. But since you're working with half a mole, um, you half that too. Since this energy belongs to a full mole of chlorine being dissociated, but since you're working with half a mole, you half it. So what that does, it gets rid of the thing, not thing, the coefficient right here, and brings this like apart basically. So what I like to think of is you multiply the coefficient by 2 and just get rid of the subscript. So 1/2 by 2 is just 1, and the subscript disappears, so it's just Cl. And you bring up the sodium, which is still a gas. And now you want to give sodium its plus charge. So that energy right there is 496 kilojoules, and that gives sodium its plus 1 charge, like I said. And you bring over the chlorine. Okay. Now you're gonna give chlorine its negative charge, and since that energy associated with it is also negative, you bring it down instead. So it's negative 349 kilojoules, and it'll look like this. Yeah. That should be it. So what you do now is you draw an arrow straight down to the base. You might want to like expand this out a little. Yeah. And that shows that these two things add up to make this. Like these two reactants add up to form sodium chloride. And the energy associated with that is the lattice energy, which is what we want to solve. So to solve for lattice energy, we rearrange the equation. The heat of formation is equal to the sum of energies, capital E, minus the lattice energy. Lattice. So to solve for lattice energy, we just rearrange this. So basically just switch these two. So lattice energy is equal to the sum of energies minus the heat of formation. So now we want to go through and add up all those energies. So you first start off with this first energy, not this, since this is the heat of formation. You'll save that for last right here. So you start off with 109 kilojoules plus half of 243, which is 125 kilojoules. Right? I know. Which is 121.5 kilojoules plus 496 kilojoules minus this since it's negative. Or you could do it like traditionally, like plus minus that, which is 349. Either way, it's minus. And finally, you subtract the heat information. So it's minus a negative energy. So in reality, you're adding it. Which should give us an energy of 788.5 kilojoules. And that would be the answer right there. So for this one, you really want to show the graph, since that's how you're basically showing your work. Um, and this equation will be given to you is kind of like something I made up, or something like Professor Schultz showed in class. So, uh, so if you want to memorize this, you can, and I recommend you do because it won't be given to you, I don't think. And that should be it for that. Okay, so number 2 says sulfur dioxide melts at negative 73 degrees Celsius and boils at negative 10 degrees Celsius. How much heat is required to convert 2.500 kilograms of solid sulfur dioxide at the melting point to a gas at 60 degrees Celsius? So for this one, um, I pulled it like straight out of the previous exam, so you should remember this. It's like that one I mentioned in the last video too, where it's like this. on. It's like this. Um, so each plateau is a phase change. And each slope is like you're heating it up, basically. So that's how you kind of want to think of it. So it says we're starting at the melting point, which means we start at a plateau right here. Hold on. Let me label this real quick. So this is going from solid to liquid. This is going from liquid to gas. In between, you're heating up the liquid here. Here you're heating up the solid, and here you're heating up the gas. So whenever you're in the phase change, like these plateaus right here, you want to use the equation, sorry, Q, Q equals the number of moles times the heat um, of either vaporization or fusion. So it's fuse slash vape, vape. And for these slopes, you want to use the equation Q equals N C delta T, the number of moles times the specific heat capacity times the change of temperature. So it says we're starting at a melting point, which means we start at this equation right here. So first let's split it up into steps. So first is we're starting at melting point, so we're converting it from a solid to a liquid. And like I said, you use the equation Q equals N times heat. A fusion this time because you're melting it. So now you want to heat it up from its melting point, which is negative 73 degrees Celsius, up until its boiling point, which is negative 10 degrees Celsius. So for that one, you use the Q equals NC delta T. Third step is you're at the melting point, or I mean boiling point, which means you're at a phase change. So you're going from liquid to gas. So since you're at a phase change, you use the Q equals N times heat of vaporization. And now you want to heat it up at the boiling point, negative 10 degrees Celsius, until you reach 60 degrees Celsius. So 4 is you go from negative 10 degrees Celsius to 60 degrees Celsius. So that's Q equals NC delta T. And that's all you're going to do for this. So we're going to plug in everything to find how much energy is required to do all that. But first of all, we want to convert the kilograms of solid sulfur dioxide into moles. Since N is moles, we're not using mass, we're using moles. So I'll do that to the side. So we start off with the number of kilograms, 2.500 kilograms sulfur dioxide. Now we convert that into number of grams. So kilograms will go on the bottom. Yeah, you guys already know this, right? And now we convert grams into moles using the molar mass, which is 64.0666 grams. That should give us 39.02 moles of sulfur dioxide. So that would be our N value. So we plug it in for this right here. Where is it? Okay. So it's Q equals 39.02 moles times the heat of fusion, which is 8.619 kilojoules per mole. Okay. Now for this, it's Q equals number of moles, 9.2 moles, times the specific heat capacity of the liquid, which is 0.995 joules per gram Kelvin. Oh, I just realized I made a mistake. Since the units here are grams, we're not supposed to use moles. We're supposed to keep it as grams. So forget what I said about the equation being N. It's actually M. Sorry about that. Yeah, I'll change it for all these. So for only these, for only the phase changes, is it N. But when we're heating it up, it's M. So we keep it in grams. So it's 2,500 grams. Sulfur dioxide. Which is what we put here. 500 grams. Because you always want the units to be the same. So if you guys like catch yourself doing that, then be careful, bro. Okay, so now it's times the change in temperature, which is final minus initial. So it's negative 10 degrees Celsius minus negative 73 degrees Celsius. So for this third one, we do use N. It's this. So it's Q equals 39.02 moles times the heat of vaporization, which is 25.73 kilojoules per mole. That should be it for that one. Sorry. Okay. Now the last step. Here we use mass like the second step. So it's 2,500 grams times the specific heat capacity of the gas, which is 0.662 joules per gram times Kelvin, times the change in temperature, which is final, minus initial. So it's 60 degrees Celsius minus negative 10 degrees Celsius. So now you're gonna want to go ahead and calculate all these energies and add them up to make a total energy. Okay, so with this, I calculated all the energies. So you add them all up to get the total amount of energy required to heat sulfur dioxide at its melting point to a gas at 60 degrees Celsius, which is this right here. It could be in kilojoules or joules, doesn't really matter since it doesn't ask. But yeah, that's it for this one. Okay, so number 3 says chromium adopts the body center cubic unit in its crystal structure. Calculate the mass of one chromium unit cell. Okay, so we know chromium. Sorry, let me write the number right here. 3. We know chromium adopts the body center cubic structure. So body center cubic. Which means it has 2 atoms in its cubic unit structure. So we want to start off with this. So this one's really easy actually. It's just 2 atoms. We just convert it into a mass. So first off, we convert it into a number of moles. So it's 1 mole of chromium is 6.022 times 10 to the 23rd chromium atoms. Avogadro's number. Now we find the molar mass of chromium and convert that into number of grams. The molar mass would be 51.9961 grams chromium. And it's just that easy. So we should get is 1.73 times 10 to negative 22 grams of chromium. Which makes sense because we're working with just 2 atoms, which means you won't have that much mass. And that's pretty much it for number 2. For these, just pay attention at which cubic structure you have because this determines how many atoms you're working with. Like if you're working with like something that has only like the simple cubic structure, then you just have 1 atom. But if you're working with like the what's it called, the face-centered structure, then you'll be working with 4 atoms instead. So just pay attention to that, and you should be good. Okay, so number 4 says draw the molecular orbital diagram and calculate the bond order of O2 minus. Is this molecule stable? Is it paramagnetic? Right, it's outer valence electron configuration. Like I said, or like for number 2, I pulled this like right out of like the exam form, so you guys should remember this. I hope. So O2, 2 minus. For these molecular orbital diagrams, you always start off by drawing it. So I'll go ahead and do that for you guys. Oh, and since we're working with oxygen, we put the pi orbital above the sigma orbital. Um, because remember um with bacon, with boron, carbon, or nitrogen, this is the bottom. But since we're not working with bacon, we're working with oxygen, it'll be on top instead. Just connect those boxes right there, like that. And we go down to this one right here. This is sigma 2s, sigma star 2s, pi star 2p, and sigma star 2p. Okay, so now we want to fill in these side boxes right here with electrons. Well, so oxygen has 6 valence electrons. There's 2 of them, so it's 12. Plus the negative charge makes 13. So we want to split those up evenly, or as even as we can, between these 2 sides. So 6 will go on this side. 1, 2, 3. Oh, sorry. Um, you start on the bottom one first. So it's 1, 2, 3, 4, 5, 6, and 7 is gonna be here on the right side. So 1, 2, 3, 4, 5, 6, 7. 6 plus 7 is 13, which is what we have. So now we want to take these electrons and fill them in from bottom to top right here. which means we start off with the sigma 2s orbital right here. So we take electrons and feed them to these middle boxes basically. So 1, 2, that's good. 3, 4. See, we took one electron from each side, and what was left over was given to this this top sigma star s 2s orbital. We do the same here. So it's 1, 2, 3, 4, 5, 6, 6. We have 2, 4, 6, 8, 9. Which means we have 3 left. So 1, 2, 3. So 3, 6, 9 electrons. Boom. That's it. Okay, so for bond order, yeah, sure, I remember this, but it's 1/2 of the bonding electrons minus anti-bonding electrons. So what bonding means, it just means like the lower half of these diagrams. So this lower half is bonding. This top half is anti-bonding. Same here. This lower half is bonding. Um, this upper half is anti-bonding. Okay, we just count up basically. So bond order is 1/2 of the bonding electrons, which is 2, 4, 6, 8, minus 2, 4, 5, minus 5. So 8 minus 5 is 3. 1/2 of 3 is 1.5. So to determine whether it's stable, we want to see the bond order. Is it greater than the 1? If it is, then it is stable. I think it's greater than the 1. Either greater than the 1 or greater than 0. I'm leaning towards greater than the 1. So, put stable. And you want to box that. So, is it paramagnetic? So, paramagnetic basically means, like, is there unpaired electrons here? Which would be yes, because see here, there's no or there is unpaired electrons. See, these are all half right here. So we put paramagnetic. Box that too. The outer valence electron configuration, we basically use these orbitals instead of like your normal like 1s2, 2s2, 2p6. Instead of this, we use these orbitals right here. The sigma, sigma star, pi, pi star ones. Okay. So for the sigma 2s orbital, you see there's 2 electrons with it. So we do sigma 2s 2. Okay. Now we move up to the sigma star 2s. Same with that one. There's 2 electrons with it, so we put 2. Now we go up to the sigma 2p. Same deal there. It's 2 electrons. Uh, and for the pi 2p, there's 4 electrons, so we do it as such. 4. And you just do it so on and so forth. So for the pi star 2p orbital, there's 3, so we do like this. And since there's no electrons in the sigma star 2p, we don't include it. See, we don't include it here. So this should be the correct answer. Okay, so 5 says, chlorine has 2 naturally occurring isotopes, Cl35, with an atomic mass of. I'm not gonna say all that, bro. And Cl37 atomic mass of that. If chlorine has an atomic mass of that, calculate the percent abundance of each isotope. Two equation, two variable problem. Okay. So some of you guys might remember this from the first exam. But yeah, I'm pretty sure I pulled it like straight from the first exam. So for this, since it's a two equation, two variable problem, we want to use the equation x plus y equals 1, and what is it? The the atomic mass is equal to the um um isotopes atomic mass times its percent abundance and the sum of that. So this for two isotopes, this expands out into what is into the mass of Cl35 times its percent abundance plus the mass of Cl37 times its percent abundance. So if you look at these two percentages, percentages add up to 1, which means uh, percentages add up to 1, which means we use this equation to add them up to 1. So instead of treating them as percentages, we treat them as variables now. So whichever one you choose doesn't matter, but I'll do percent abundance for 35 as x, the percent abundance for 37 as y. With that being said, we replace that for these. Oh, and it's all equals the atomic mass of chlorine, which is 35.4527 mu. Okay, so we bring it down, we put the masses here, and we put the x's as the percentages instead. So for 35, it's 34.9689 AMU x plus the mass of 37, which is 36.9659 AMU y. And that equals the mass of chlorine. Okay, so to solve for the percent abundances, we have to solve for just 1% abundance first, which means to solve for just one variable first. So whichever one you choose doesn't really matter, but here I'll solve for y first, I guess. So we arrange it to say y equals 1 minus x. So wherever we see y, we're going to replace it with this instead. So this is going to replace this y right here. Okay, so let's rewrite it. 34.9689 MUX plus 36.9659 AMU times 1 minus x. So equals that. So now we want to distribute this mass into 1 and minus x. So that'll give us, I gotta rewrite it again. So 36.96, or I mean 34.9689 AMUX plus 36.9659 AMUX. Oh, sorry. Just AMU minus 36.9659 AMUX. Okay, so since these are like terms, they share the x variable. We subtract these two, and we leave this for now. That subtracts out to be negative 1.997 AMUX plus 36.9659 mu. And you bring down the atomic mass of chlorine. So it's 35.4527 mu. So now we just want to solve for x. So first we start off subtracting this mu from both sides. Minus 36.9659 mu. So that gives us negative 1.5132 mu equals negative 1.997 mu x. Okay, so to isolate x, we divide both sides by negative 1.997 mu. Okay, so that should give us x equals 0.7577. Okay, and that would be our percentage. So as a percentage, it would be 75.77%. So that's the percent abundance for, what is it? For chlorine 35, Cl35. Okay, and to solve for the second percent abundance, we just take this number and plug it into the equation y equals 1 minus x. So y equals 1 minus 0.7577. That'll give us 0.2423. And as a percentage, that's 24.23%. And that would be the percent abundance for chlorine 37. So the hardest part for this is just starting off with the equation. You see, it's a lot of steps. But once you get the first percent abundance, the second one should be the easiest to find, since you're subtracting what you get from one, basically. Here. And yeah, that should be it. Okay, so number 6 says, the multi-step smelting of ferric oxide, iron 3 oxide, to form elemental iron occurs at high temperatures in a blast furnace. In the first step, ferric oxide reacts with carbon monoxide to form iron, I don't know, Fe3O4. That this substance reacts with more carbon monoxide to form iron 2 oxide, which reacts with even more carbon monoxide to form molten iron and carbon dioxide. Carbon dioxide is produced in every step. So for the first question, it says, write a balanced equation for all steps as well as the overall balanced equation. So let's do that first. So 6a. So there's 3 or 4 steps in here. The first one is ferric oxide. So iron 3 oxide reacts with carbon monoxide gas to make Fe3O4, as well as carbon dioxide. And for these, you want gas for carbon dioxide and carbon monoxide, and liquid for these, since they're in a furnace. They're being melted together. Okay, so that's the first step. Second step is you melt this product with even more carbon monoxide. So it's Fe3 H3O4 liquid with carbon monoxide. That makes iron 2 oxide, which is just FeO. FeO. That's liquid too. Pretty sure that's liquid. Let me check real quick. But carbon dioxide is also produced. Okay, I just checked and it is liquid here. Okay. So that third step is the iron 2 oxide reacts with even more CO2. Sorry, liquid. With even more CO, I mean. And, make the molten iron. So Fe liquid. And that also makes CO2 gas. Okay. So now we want to go through and balance these. So there's 2 irons on this side, 3 here. So we find the common multiple. It's 3, 2. So that's good. And there's 8, 10, 9, 10 oxygens. That's good. There's 1 carbon, 1 carbon. That's good. Here, there's 3 irons. 1 iron. So you put a 3 here. And 4, or I mean 3, 5 oxygens. 4, 5 oxygens. That's good. And 1 carbon, 1 carbon. That's good. So that's all you need to do. And here there's 1 iron, 1 iron, 2 oxygens, 2 oxygens, 1 carbon, 1 carbon. So that's good too. But now we want to like combine these to make an overall equation, which means whatever's on the opposite side of these is gonna be canceled out. So like this Fe3O4, they're on both sides of this equation, or like opposite sides of the equation, which means we cancel these out too. Same with these iron 2 oxides. Okay, so we want to put a 2 coefficient here to match the number of this side onto the right side. So those cancel out. Actually, but first we want to balance it now. Again. So this, actually, you know what? Yeah, I'll bring it over. So 1 is the same. That's good. Now we want to balance this newly created one. So now there's 2 Fe3O4s, which means we want to balance out this right side to match that. So there's 6 iron here, which means we want to put 6 Fe's here. FeOs, I mean. Okay, so that's 6 iron, 6 iron. Now the oxygen is 8, 9. And here it's 6, 8. Yeah, 6, 8. So we want to like find like common ground between these two. Um, you can't really like do it like as like process. There's no like good way to do this. You just kind of like gotta play with it, like to find the answer. For these, it's pretty simple. It's just two right here. So it makes 8, 10, 6, 10. And there's two carbons and two carbons, so that's good. Okay, now let's go back here. So these two cancel out. Yeah, let's just show that. And now we want to cancel out these iron 2 oxides. So we want to put a 3 coefficient here. So let's bring that down. So 3, or sorry, it's a 6 now. Or sorry, it's a 6 now because now there's 6 iron 2 oxides here. So instead of a 3, you put a 6. And CO2 again. Oh, sorry, I forgot to balance this one, but it's 3. My bad. Okay, now CO2 gas. So there's 6 irons here. We're gonna put 6 here, and the rest is the oxygens. So it's 6, 7, and there's 2 here, which means we want. So we want to put a 6 coefficient in front of this. Sorry. Um, Let me make it clearer. 6 coefficient in front of this, and a 6 coefficient in front of this. So that makes 6 carbon, 6 carbon. That's good. So 6 oxygens, 12 in total on this side, and 12 here as well. 6 times 2 is 12. So that's good. Okay, so now we can go ahead and cancel these out. Okay, so what's left is going to be the overall equation. So overall is 3 iron 3 oxides plus 9 carbon dioxides make 6 molten iron and 9 carbon dioxides. And we can check this by just counting what's on both sides. So there's 6 irons here, 6 irons here. 9 18 iron or 18 oxygens on this side, 18 here, and 9 carbons, 9 carbons. That's good. So this is oh this is your so this is your balanced overall equation. Okay, so this is what we're gonna use in the next step. But first, what do you notice here? What do you notice about the coefficients for this balanced chemical equation? They can all be simplified into multiples of 3, which means this isn't where we stop. We actually go like kind of further than this. Let's erase this real quick. Okay, so you just want to simplify it even more. So I'll just draw it over here. So just divide all the coefficients by 3, since that's literally like what you could like do with these coefficients. You can simplify them and still retain the same formula. Not formula, but like balanced chemical equation, you know. So it's just 1 mole of ferric oxide or iron 3 oxide, same thing. And now instead of 9 moles of carbon monoxide, it's 3. And that makes just 2 moles of iron and 3 moles of carbon dioxide. Yep, now you're done with this. And this is what you use for the next step, B. So that question asks, how many grams of carbon monoxide are required to form 45.0 metric tons of iron from ferric oxide? So this is just a simple stoichiometry problem. So we're starting off with metric tons of iron. I'm sure there's a unit for metric tons, but I just wrote it like this. So we want to convert that into kilograms of iron, then grams, then moles of iron, yeah, then moles of carbon monoxide, then grams of carbon monoxide, and you're done. So let's do that. So 45.0 metric tons of iron. So if you look at the last page of study guide, there's a unit conversion for metric tons to kilograms, and it's 1,000 kilograms per 1 metric ton. Okay, now we've got to convert to grams. It's 1,000 grams for 1 kilogram. Yeah. Now we convert into moles using the molar mass, which should be 55.845 grams of iron. Okay. Now we use this equation right here to get a ratio of carbon monoxide to iron. So see, for every 2 moles of iron, there's 3 moles of carbon monoxide. So on top is 3 moles so we're converting to of carbon monoxide. And on the bottom there's 2 moles of iron. Okay. And now we convert into number of grams of carbon monoxide using the molar mass, which is 28.01 grams. Okay, so doing all that, we should get a value of 33 million 900,000, or 3.39 times 10 to the 7th grams of carbon monoxide. And that should be what you should be getting. So these multi-step ones are pretty confusing since you gotta like shuffle around coefficients and stuff. But if you keep track of everything, it should be easy. Or easy-ish, I mean. Okay, so number 7 says, use the enthalpies of reaction above to calculate the standard enthalpy of reaction of N2O3 gas plus N2O5 solid makes 2N2O4 gas. So this top equation is what we want to work towards. N2O3 gas plus N2O5 solid. Make 2 N2O4 gas. So let me just go ahead and copy over all of the equations real quick. Okay, so I copied everything over. Now let's work towards this top equation. Okay, so let's start off with the N2O5. We want it to be solid, which means we want this solid one to stay on the left side. So this is good. We don't want to change this. Okay. Now the N2O3 gas. Is located on this side, on the right side, not on the left, which means we want to flip this. Okay. Now the 2NO4, it's on the right side, but it's only one right here. So we want to double this. Now we want to cancel out everything else that's not these three right here, since these are part of the final equation, so we don't want to get rid of them. So you can see here for the bottom, the N2O5 gas is on the right. There's one on the right side here. So in order to get rid of one of them, we want to flip this one. Since we don't want to flip this one, since the N2O5 solid is already on the correct side. So let's go ahead and do that. So I'll bring everything down and rewrite it real quick for you guys. Okay, so now I've done everything I had to. So I flipped the first two equations like I said. See, the gas right here is on the other side now. So let's box that again since we don't want to lose it. The second equation is also flipped. You see the product here is now the reactant. I doubled this equation, or no, it's 4 NO2s and 2 NO2 4s, or and 2 O4s. Sorry. Okay, so we want to keep that. I didn't do anything to this equation just yet, and this one was always good from the start. Okay, now let's see if everything can cancel out. So first off, these two cancel out right here. Okay. These two NOs add up to 2, and they cancel out this 2 NO. This O2 gas as well cancel out. And there's 1, 2, 3, 4 NO2s. They all cancel out with this. So turns out we didn't even need to move this fourth one. Okay, now this overall equation is going to be, oh, it's kind of ugly. It's going to be basically the same as the top equation right here. So it's N2O3 gas plus N2O5 solid makes 2N2O4 gas. So that's good. Okay, now for the enthalpies of reaction, we want to do what we did to the equations onto them. So for a flip, we flip the state, or not the state, but the sign here. If it's negative, it turns positive. So since that is negative right here, it turns to a positive 39.8 kilojoules. Same for this bottom one. It got flipped, so we flipped the sign as well. So that's positive. Positive 12.5 kilojoules. Now this one, we doubled the coefficients here, which means we double this one as well. So that is, I think, up negative 114.4 kilojoules. Okay, and these bottom two were unaffected, so we just leave these like this. So to find the heat of reaction for this equation, we want to add up all of these energies for one total energy. Okay, so what you should be getting is negative 22.2 kilojoules. So that'll be your answer right there. Yeah, that's the standard enthalpy of reaction for this equation. And that should be it for this problem. Okay, so number 8 says, aspirin is made by reacting salicylic acid with acetic anhydride, which has a density of 1.080 grams per milliliter, through the following reaction. In one preparation, 3.067 of salicylic acid and 5.67 milliliters of acetic anhydride react to form 3.281 grams of aspirin. What is the limiting reactant? Calculate the percent yield. Okay, so this is a limiting reactant problem, which means we use stoichiometry again. So we start off with each reactant. We're given 3.067 grams of salicylic acid. I'll write it like this: sal acid, because I don't want to write all that. So we want to convert that into the number of grams of our product, which is aspirin. So we want to convert this into a number of moles of salicylic acid first. So 1 mole sal acid is equal to 138.122 grams of salicylic acid. Okay, now we want to use stoichiometry to just convert from moles of salicylic acid into moles of aspirin. Luckily it's all 1-to-1, so it doesn't matter. Mole aspirin and 1 mole of salicylic acid. Now we convert this number of moles of aspirin into a mass of aspirin, using the molar mass, which is 180.159 grams of aspirin. Over 1 mole of aspirin. Okay, that should be it for that. Let's put a pin on that and go to the other reactant, which is 5.67 milliliters of acetic anhydride. I'll put like double A, acetic anhydride. I don't really want to write all that, but on your exam you should write like a lot of it, like shorten it down to like sal acid or something like that. For this, we don't start off with grams. We start off with milliliters, which means we want to utilize the density given to us. 1.080 grams for every 1 milliliter to convert into grams of acetic anhydride. Okay, from there, we just follow the same steps as this, basically. We convert into number of moles of acetic anhydride using the molar mass, which is 102.089 grams. That. Then to the number of moles of aspirin, which is the same as this top one. It's all 1-to-1. Like I said, you're expected to write the whole formula of aspirin, or at least like a full word like this aspirin and not like double A like this for acidic anhydride, because Schultz is kind of picky about that. Probably. Okay, now we just use the molar mass to convert into number of moles, or I mean grams, sorry, of aspirin. Aspirin. Okay. So for this top one, we we get 4.000 grams of aspirin. And for this bottom one, we get 10.81 grams of aspirin. So to find the limiting reactant, we just look at which reactant gave the least amount of aspirin. So it's obviously 4.00 grams of aspirin here, which makes this the theoretical yield, Ty, and 3.067 grams of salicylic acid are the limiting reactant. So just want to box that. The limiting reactant is the one like that made the number of the product, not the other way around. So this wouldn't be the limiting reactant; it'd be this. Well, it's a common mistake sometimes. Okay, so for the percent yield, it's the actual yield divided by the theoretical yield. So our actual yield is 3.281 grams of aspirin. You don't gotta put aspirin since like it's gonna cancel out anyways. So grams is fine, but yeah, over 4.000 grams of aspirin. That's 100%. Sorry, I forgot to put that there. 100%. That should give us a percentage of 82.03%. So that's our percent yield for this palm. That should be it. Yep, it's just that easy. Okay, so 9 says methane CH4 has a boiling point of negative 164 degrees Celsius at 1 atmosphere and a vapor pressure of 42.8 atmospheres at negative 100 degrees Celsius. What is its heat of vaporization? Okay, so this problem uses the Clatch-Clapeyron equation, which is given to you in the last page of the study guide. It's ln of P2 over P1 equals the negative heat of vaporization over R times the inverse change in temperature. So 1 over T2 minus 1 over T1. Okay, so to solve for the heat of vaporization, we just rearrange this whole equation to like one to solve for this basically. So you guys should remember this from your exam. So if you're confused on how to rearrange the equation, I'll show you. But first, we want to divide both sides by the inverse change in temperature. So it'll be like this. Natural log of P2 over P1. Let me zoom in real quick. Divided by the inverse change in temperature. Equals the negative heat of vaporization over R So now multiply both sides by R. That makes ln P2 over P1 times R over the inverse change in temperature equals negative heat of vaporization. And to get rid of this negative, just divide both sides by -1. So heat of vaporization equals negative all of that, right there. So negative ln P2 over P1 times R divided by the inverse change in temperature. So this is how I like to do it, but Schultz does it like this. Here, I'll show you. Or formats it like this. So he does all of like the fractions right here as inverses. So the inverse change of temperature is just like this to the -1 power. Since -1 is equal to like being a fraction. So all this times the natural log of P2 over P1. Whichever way works for you best. I prefer it this way, since even though it seems like kind of like chunky and like hard to follow, I do it all like step by step. But like to each their own, I guess. Okay, so to solve for the heat vaporization, we first have to assign numbers to the pressures and temperatures. So you see the problem, it says has a boiling point of negative 164 degrees Celsius at 1 atmosphere. We treat that as our P1 and our T1. So P1 is 1 atmosphere, and that's tied to the boiling point, which is negative 164 degrees Celsius. And it says it has a vapor pressure of 42.8 atmospheres at negative 100 degrees Celsius. So we treat that as our P2 and our T2. 42.8 atmospheres, negative 100 degrees Celsius. And now we convert each temperature into a temperature in Kelvin. Since the R value is in joules over moles times degrees Kelvin, we want the Kelvin or the temperature unit to be the same for both. So we add 273 to both of these temperatures. So this is 173 degrees Celsius, and this is 109 degrees. Oh, sorry, I mean Kelvin. Kelvin, 109 degrees Kelvin. Not degrees, it's just Kelvin. Sorry. So this is what we'll plug in to this equation right here. So I'll do it my way. It's the heat vaporization is negative LMP2, which is 42.8 atmospheres, over P1, which is 1 atmosphere, times R, which is given to you. It's 8.314 joules over moles times Kelvin. So all that divided by the inverse change in temperature, which is 1 over T2, which is 173 Kelvin, over over T1, which is 109 degrees, or sorry, not degrees, just Kelvin. So all that should give us a heat of vaporization of 9,200 joules, or 9.2 joules. kilojoules, I mean. Whichever one, since it doesn't ask for a specific unit. But that should be it for number 9. Okay, so number 10 says, state the N, L, and ML values of each subshell. So this is pretty easy in my opinion. So N is just period number basically. Like if you look at your periodic table, the rows right there are each period numbers, and they increase as you go down. L is your subshell. I think of S, P, D, F. Each one of these letters is tied to a number. So S is 0, P is 1, D is 2, and F is 3, and so on. I think G is next. It's 4. I think H is 5. Yeah. So and so on. You won't really get past G, I'm pretty sure. But yeah. And ML is just the negative to positive range of your L values. So negative up until positive L. Like if your L value is P is 1, then your ML values are -1, 0, and +1, like that. So with that being said, let's look at A. So A is 6P. So that's kind of ugly A. A is 6P. Okay, so N is your period number, 6. L is your letter P, which is 1. So your ML is -1, 0, and +1. That's it. It's just that easy. Wait. So yeah, let's do B. So B is 4F. So right off the bat, N is 4. Okay. L is 3 right there. So your ML values are is the negative up until the positive range of your L value. So -3, -2, -1, 0, +1, +2, +3. Boom, like that. Okay. Now C. Here, I'll do it on top right here. So C is 5G. So N is 5. L is 4. G is kind of uncommon, but you will see it. Or you'll probably see it like sometime in the future. So your ML values is just the negative to positive range. Boom. Oh, sorry. It's just that easy. So this is kind of what like is something you should expect on the exam. I don't know like if it'll be as easy as this, but it'll prepare you for like what's to come, basically. Okay, so 11 says identify the oxidizing and reducing agents of each reaction or for each reaction. Let me go ahead and copy each reaction down first. So to find the oxidizing and reducing agents, you want to see which species is being oxidized and reduced. So, so if it's being oxidized, it means it's losing electrons and giving it to something else, which means it's reducing the charge of something else, which means it's the reducing agent. Something like that. And if it's being reduced, it's gaining electrons. It's helping something be oxidized, which means it's the oxidizing agent. Okay. So which of these species is being reduced and which is being oxidized. I can't hear your answer, so I'll just say it for you. So copper is going from a 0 charge, it's charge neutral here, up to a +2 charge. So copper going from 0 +2. That is oxidation. So if it's being oxidized, that means copper is a reducing agent. I would box that, I guess, and box copper. Or you could be like, reducing agent equals Cu. Yeah. Okay. And look at nitrogen here. So the oxygen is always going to be -2 unless it's in a peroxide. But here it's not in the peroxide, so it's -2. There's 3 of them, which means in total it's -6. So the charge on the molecule is -1, which means you want the nitrogen have a charge or an oxidation number that reaches -1 from -6. So -6 plus what makes -1? It's +5. Okay, so nitrogen is going from +5 to just +2 here, since there's only one oxygen. So nitrogen is going +5 to +2. But when you're looking at agents, you want to highlight the whole species or the whole molecule is a part of, not just the single atom involved. Like for reducing agent, it was copper, but that's by itself. So that's why it's only just copper. But here it's nitrate, which means oxidizing agent is nitrate right there. And I guess you can also include the states of matter. So copper was solid and nitrate was aqueous. Okay. So that's how you find the reducing and oxidizing agent. So here, I'll just do it for you guys. So this one is a peroxide. And it's one of peroxide, yeah. And it's the only exception where oxygen is just -1, not -2, like how it was for this first problem. So oxygen goes from -1 up to -2 right here. So it's going back to normal. So this means it's being reduced. So it's the oxidizing agent. But not just oxygen though. It's the oxidizing agent is peroxide. So we put the H2O2 instead of just H or um oh I mean like that. Okay, now look at iron. It's going from a +2 to a +3. So it's being oxidized, it's the reducing agent. And for this one, you include the charge of the original species you're looking at. So Fe +2, not +3. Oh, sorry. So this is how you find oxidizing and reducing agents. Just look at a change in oxidation number. And that's it. It's that easy. Okay, so number 12 says, which hybrid orbitals and bond types form around the following molecules? So let's look at A first. 12A is N3 minus. So to find the hybrid orbitals and bond types around the centron, we first have to draw the loose dot structure of this. So just one end surrounded by two ends on both sides. Okay, but first let's count how many electrons we could work with. So nitrogen has 5 valence electrons. There's 3 of them. And with the addition of the negative charge right here, that means in total we have 16 electrons to work with. So we'll start off by filling in each outer atom with 8. Okay, so that's 16 right there. But you see, this central nitrogen doesn't have 8 10 electrons. So we bring in 2 from each side. Okay, now it's 2, 4, 6, 8, 10, 12, 14, 16. That's good. But now it's missing a lone pair here. So instead of that, we give it a double bond right here, or a triple bond. Everything's good. We use 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. Okay, now let's see if the former charges check out. So remember, for former charge is your atoms number of valence electrons minus the sum of lines and dots around it. That's just like another like simplification of like bonds and lone pair electrons. But I like to simplify it to just lines and dots since it's easier to follow. So for this right end, there's 1, 2, 3, 4, 5. That's a 5. See, nitrogen has 5 valence electrons, so the charge is 0 right here. So that's fine. And for this nitrogen in the center, it's 1, 2, 3, 4, 5. 5 as well, which means it's charge neutral as well. And for this nitrogen on the left, it's 1, 2, 3, 4, 5, 6. 6. 5 minus 6 is -1, which means the negative charge for the molecule is coming from this, which is good, because we want the least number of atoms in the molecule to have a former charge. So this is, in my opinion, the best way to write it. So now we want to look at the center atom, this one in the middle. So there's 2 sigma bonds, and 3 pi bonds. So 2 sigma, 3 pi. The sigma only count, not only, but with the lone pairs. Sigma and lone pairs only count towards hybridization, not pi bonds. Which means the hybridization for this central atom is just sp1. That's it. So this is the hybrid orbitals, and these are the bond types. Okay, now for B, it's CH3 CCH. So first, let's draw the Lewis dot structure. So CH3 C triple bond CH. This probably has a name to it, but I don't remember like off the top of my head. Okay, so now we have 3 central atoms right here. So let's try to find the one, or the hybrid orbitals and bond types around this first one. So C1, there's 1, 2, 3, 4 sigma bonds. Which means this is sp3. Okay, so that's good. Now for the second one, there's one, two sigma bonds, and two pi bonds. So it's 2 sigma, 2 pi, sp1. Okay. Now for this third one. Oh, sorry, I didn't draw correctly. That. So you see, it's the same here as C2. There's 2 sigma, 2 pi. So it's basically just the same thing. It's sp1. And that's it for this. These are pretty easy as long as you know how to draw the Lewis dot structures. Just remember you want the least number of atoms in the molecule to have a form of charge if there is a charge involved. But for this one, there wasn't a charge involved, so you were good with that. Okay, so 13. It's your first OChem question. It says, write equations for the following organic reactions. So let's start off with A. It's 1 iodopropane reacts with sodium hydroxide to form propanol and sodium iodide. So for this, we want to write the full formulas, not calculus structures like this. It's full formulas. So instead of this, you want like CH3, CH2, CH2, CH3, that kind of stuff. Okay. Let me erase that real quick. Okay. So for the first one, 1 iodopropane. The iodo means there's an iodine present somewhere. The 1 dash means it's present at the first branch of the molecule. The prop means there's 3 carbon backbone. And the ane means they're all single bonds. So I'll draw a calculus structure to make it simpler to understand, but for the exam you don't want calculus structures, you want to draw the full equation. Okay, so 3 carbon backbone is 1, 2, 3, that's it. And the iodine is just right here. Doesn't matter whether it's here on the right or here on the left, since either way it starts at the first branch. See, this could be treated as the first branch, or this could be the first branch. It's all the same. So let's write this as a formula. So this little point is a CH3. This is CH2. And a CH2 as well. And the I right here. Okay. Here, I read it in as a Lewis dot structure to make it a little easier to understand. You guys are still confused. So this is the CH3. It's bonded to a CH2. Yeah, that's bonded to a CH2. Oh, sorry. And that's bonded to an I. So these are all the same, basically. Just a different way of writing it. But Professor Schultz wants you guys to write it like this. Okay, so let's work off of this then. So this reacts with sodium hydroxide. Okay, to form propanol and sodium iodide. So basically, just think of this. This hydroxide has a negative charge, as you know. Just switching places with this iodide, basically attacking it. since you know one of the products is sodium iodide, that means in the end you want sodium and iodide to be together, which means OH has to be away from sodium and switch places with the iodide here. It's kind of how like I see it. So now we want to rewrite it. OH plus sodium iodide. For these alchem questions, you don't gotta put like states of matter since Professor Schultz isn't really like looking for them for this type of thing, but it kind of helps, I guess. So this is the valid answer for that. It's basically like a glorified like chemical reaction. You know, all of this stuff right here is basically filler. Filler. The only interesting part is what happens at the ends here. And you see here the OH makes an um a null suffix, which supports which supports the fact that we have propanol. See, prop is a 3-carbon backbone, yeah, and the anol is uh, um the alcohol group right here. So that just like supports like the idea that we got it right, basically. So B now. One butene reacts with hydrogen gas to form one butene. Platinum is a catalyst. Okay, so but means 4. Okay. The "-ine suffix means it's a triple bond somewhere. And the 1 dash at the beginning of that means the triple bond is located at the first branch of this molecule. So let's draw it like that. Like I'll start off with a calculus structure to like simplify it. So but 4, 1, 2, 3, 4. Ine is the triple bond. The 1 dash means it could be either here, here, or here. I prefer this way, but you can draw like that either way. So let's draw this as an actual formula. So it's CH C CH2 CH3. I'm pretty sure. Um let's write this as a loose dot structure. So it's C with um, a triple bond to another C H. Then this is bonded to another C H2. This is finally bonded to CH3. Yeah, that's good. Okay, so this reacts with hydrogen gas to form one butene. So um the root of but stays the same, but the thing that changes is the ene. So the ene suffix means there's a double bond somewhere in the molecule. And the 1 dash right there, beginning of it, means it's in the first branch, like this one right here, basically. So I'll draw a structure right here. Boom, that's it. Or it could be, yeah. So this is what that makes. It's C H CH2 to CH to CH2 CH3. Pretty sure that's how it's done. Well, let's just verify by doing a Lewis dot structure. So CH2 double bond CH. Yeah, that's good. 2, 4, 6, 8. Yeah. Yeah, that's good. So this is what you should be getting. Um, and the platinum as a catalyst part is just this. So if it says it uses something as a catalyst, it just means like this is going on top of the equation arrow. And that should be it. And I just realized this, but I put an extra line right here for N3 minus. For some reason, I thought the N had to reach 10 electrons, but it's just 8 right here. Sorry about that. So this just changes into that. And that gives this a positive charge and this -2 charge. So even though we want to avoid the least number of charges present, uh, we can't help it sometimes. Just just redraw it like better. So regardless, it stays the same. There's still 2 sigma bonds right here. So the hybridization doesn't change. But the number of pi bonds does. It's just 2 now. So sorry about that. I think that should be all for the errors. Okay, so number 14 says when 25.0 milliliters of 0.500 molar sulfuric acid is added to 25.0 milliliters of 1.00 molar um potassium hydroxide in a coffee cup calorimeter at 23.50 degrees Celsius, the temperature rises to 30.17 degrees Celsius. Calculate the change in enthalpy of water formed in kilojoules per mole. Assume the total volume is the sum of the two volumes and that the solution's density and heat capacity is the same as that of water. Okay, so let's shelf the volumes of sulfuric acid and potassium hydroxide for a second. Let's focus on the total volumes. So it says the total volume is the sum of the two volumes. So actually, let's take those volumes out of the shelf real quick and work with those. So total volume is just 25.0 milliliters plus 25.0 milliliters. So that's obviously 50.0 milliliters. Okay, so this, we assume that the solution has the same density as water. So, so we convert this into the number of grams of water. So the density of water is just 1.00 grams per 1 milliliter. So that just gives us 50.0 grams of water. Okay. So we use this in tandem with the Q equals mc delta T equation to solve for the heat, like absorbed basically. Well, maybe not absorbed, but just heat in general. So we have a mass. The specific heat capacity we're told is the same as that of water, and the temperature is given to us as well. So we'll plug those in real quick. Q equals mass, 50.0 grams of water, times its specific heat capacity, 4.184 joules over grams times degrees Celsius, times the change in temperature, which is final temperature, 30.17 degrees Celsius, minus initial temperature, 23.50 degrees Celsius. Okay, so solving for the heat, we get 1395 joules. But since we want the change in enthalpy in kilojoules per mole, we want to convert this to kilojoules. So just 1.395. You can run this to 3 sig figs if you want, but if you do round it, you'll only get like 2 sig figs since it'll be like this, since you round this up. So you don't really have to. It won't affect your numbers that much. So I just keep it like this, low key. Okay, so now we've got kilojoules, and we want an answer in kilojoules per mole, which means we want to find moles. And we won't find moles from this. We'll find moles by using the volumes and molarities of sulfuric acid and potassium hydroxide to find moles. So this is another um, stoichiometric type situation. So we start off with 25.0 milliliters of H2SO4 sulfuric acid. Okay, we want to convert that into the number of moles of water, which actually means first we have to do a balanced chemical equation. So H2SO4 aqueous reacts with KOH aqueous. So this is an acid-base reaction, and from that we always get water and the salt. So the salt would be potassium sulfate aqueous and water. So to balance this, we just put a 2 in front of potassium. There's 2 potassiums here, and only 1 here. And that makes 4 hydrogens. So we put a 2 right here to make 4 as well. And I think that should be good. 2 oxygens, 6, 2, 6. Yeah, that's good. Okay, so with this, now we can convert the volumes to moles. So 25.0 milliliters of H2SO4. So to convert that to number of moles, first we gotta start off with by converting it into a number of liters. Okay, so 1 liter, 1,000 milliliters. Okay, so from here we can use the molarity given to us, which is 0.500 molar. So that expands out to be 0.500 moles of sulfuric acid for every liter. Okay, so from there, we can convert moles of H2SO4 to moles of water using this equation right here that we just did. So for every 1 mole of H2SO4, there's 2 moles of water. We can use that as a ratio. So 2 moles of water and 1 mole of sulfuric acid. And we stop there. Usually in stoichiometry problems, you would convert this to number of grams, but since we want kilojoules per moles, we don't want to convert to grams. Now let's do the same for the other one because we want to find out which of these volumes gives us the least amount, since that would be technically our theoretical yield. So that's what we'll use. So same volume of potassium hydroxide. Oops, sorry. KOH. It's basically just the same deal as we did for the sulfuric acid. We convert it into the number of liters, and from there we use its molarity, which is just 1.00 per liter. And we find the ratio. It's 2 to 2. So it's 2 moles of water for every 2 moles potassium hydroxide. You can simplify this down to just 1 1. Well, doesn't really matter like what how you do it. So I'll just keep it like that. Okay. So doing the math, you see we actually get the same number of moles of water for each of these. So 0.0250. So I added a 0 here because we want to keep the same number of sig figs, 3 here. So 50 moles of water. So it doesn't matter which one we choose, it'll be the same outcome. So we take our kilojoules and divide it by our number of moles. So the change in enthalpy is equal to 1.395 kilojoules divided by 0.0250 moles. So that should get you 55.8 kilojoules per mole. And that should be it for this problem. Okay, so number 15 asks, carbon disulfide CS2 has a boiling point of 46.2 degrees Celsius and a freezing point of negative 111.5 degrees Celsius. What are the boiling and freezing points of a solution consisting of 8.44 grams of phosphorus P4 dissolved in 60.0 grams of carbon disulfide? And we're given the constants for the boiling and freezing point. So this type of problem is one that uses molality, which instead of molar, which is moles over liters, you use moles over kilograms instead. Okay, so for this, we want to have moles of whatever is being dissolved in a solution divided by kilograms of whatever is dissolving that. So it says the 8.44 grams of phosphorus P4 is being dissolved. So that'll be what we like turn into a number of moles. Okay. And the 60.0 grams of carbon disulfide is the solvent. So it's what's like dissolving potassium right here. So that'll be what we convert into number of kilograms. So it should be pretty easy. It's just kilograms from grams. So it'll be 0.0600 kilograms of CS2. And for this, we solve for number of moles, like I said, by using the molar mass, which is 123.896 grams. P4. Squeeze that in there. So, solving for that, I got 0.0681 moles of potassium. Or, I mean, phosphorus. Okay, so combining these two, we want to solve for molality. So, like above says, molality is moles of solute, which is moles of our phosphorus, divided by the kilograms of our solvent, which is the kilograms of our carbon disulfide. Sorry, let me just expand this real quick. Okay, so that should equal 1.135 mole 0.13 mole of potassium. I mean phosphorus. Sorry. So let's start off by solving for the change in boiling point. So if you look at the back page of the study guide, you're given the formula delta TB is equal to KB, or constant, times our molarity, or molality. Sorry. Okay. So let's just plug the numbers in since we're given everything here basically. So change in TB is equal to 2.34 degrees Celsius over molality times our calculated molality, which is 1.135 mole. You can bring over the P4 if you want, but it's not really necessary. Okay, now let's save that for later and let's do the formula for the freezing point change. So it's basically the same thing as the one above. It just changes constant, which is also given to us. So 3.83 degrees Celsius over molality over mole times our molality, which is 1.135 mole. Okay, so let's solve for this. So for change in boiling point, I got 2.66 degrees Celsius. And for the change in freezing point, I got 4.35 degrees Celsius. Okay. So with these, we're going to use the freezing and boiling point given to us to add this to the boiling point and subtract this from the freezing point. So let's start off with the boiling point. The boiling point given to us was 46.2 degrees Celsius. So to this, we add what we calculated for the change in boiling point, this right here. Since with colligative properties, in most cases, you're raising and you're lowering, or you're raising the boiling point and lowering the freezing point. So this will give us 48.86 degrees Celsius. But since we're adding, we round to the lowest number of decimal places, 3. So in reality, it's 48.9 degrees Celsius. So that's our new boiling point. Now for the freezing point, it's negative 111.5 degrees Celsius. So to this, like I said, we subtract what we found here, the 4.35 degrees Celsius. That should give us negative 115.85. But again, since we're running to one decimal place, it rounds up to negative 115.9 degrees Celsius. And that should be it for this. So keep in mind, for these problems, you'll want to work with molality, not molarity. Okay, number 16 says, write the condensed electron configuration of the following transition metal ions. Draw partial orbital diagrams for the valence electrons and state whether they're paramagnetic or diamagnetic. Okay, this is pretty easy. So 16A is a copper plus 2 ion. Okay, so let's start off by drawing the full configuration. Actually, just condensed. Sorry. So the noble gas before copper is argon. So we start off with argon in brackets, and work our way up towards copper. So we leave off on 4s2, go into 3d 9. But since copper is an exception to this order, we actually get rid of the 1 or the 2 here, put a 1, and bring that extra electron over to the d orbital to make it 10. So since this copper ion has a plus 2 charge, we want to take 2 electrons away from its valence electrons. So we first start off with the period number that's the highest, which is 4s1. So we take one away from there, and now that we're um done with that subshell, we move on to the next highest level, which is 3d. So from there, we take the 1 electron we need and transform this into the correct configuration, which is argon 3d9. So with transition metal electron configurations, if the charge like exceeds what's like on your highest period number, you move on to like the next like highest in power period number basically. Which is what I did here. I took away the one from the 4s subshell, and I took one more from the 3d subshell, make 3d9. So this is a good configuration. Okay, so now let's draw a partial orbital diagram, which is just drawing the orbitals present in this configuration. So just draw the d orbital basically. Like that. So there's 9 electrons. So we start off by filling in each box. 5, 6, 7, 8, 9. This is the 3D subshell. So do you guys think this is paramagnetic or diamagnetic? Well, paramagnetic means there's unpaired electrons present, which is definitely the case here. Diamagnetic would mean that there were no unpaired electrons, like this, but that's not the case. So that means this is paramagnetic. Just box it like that. Now for B, we're working with iron 3 plus ion, so Fe plus 3. So same with copper right here. It starts off at the 4s subshell, since it's um, uh, um the previous noble gas passed was argon. So 4s 2 and 3d6. Okay, so unlike copper, this does fill regularly. There's 2 electrons in this subshell. So with the plus 3 charge, we take away 2 electrons to get rid of this subshell, since it's the highest period number, it's the highest energy level. And we take away 1 from here. So it'll be argon 3d5. That should be it. So now let's draw the partial orbital diagram for this. 2, baby. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 electrons. This is very obvious that's paramagnetic since all 5 of these electrons are unpaired. And this should be it for number 16. So 18 says an experiment requires 50.0 milliliters of a 0.040 molar sodium hydroxide for the titration of 1.00 millimoles of an unknown acid. Mass analysis of the acid shows 40.0 mass percent carbon, 60 or 6.71 mass percent hydrogen, and 3.3 mass percent oxygen. Find the molecular formula of the acid. Okay, so this is like I asked for. It's a molecular formula problem. So what we start off with is we find the imperial formula first. To do that, we convert every mass percent into a number of grams, and then into a number of moles. So a percentage is out of 100, and we can use that to convert the percentages given to us, like 40.0% carbon into number of grams out of 100. So since it's 40.0% out of 100, we convert that into 40.0 grams out of 100. It's kind of like mental gymnastics, I guess, but that's how it's done. Okay, so now it's that for rest of it's 6.71 grams of hydrogen and 53.3 grams of oxygen. So now we convert these into number of moles using the molar mass. So even though it's just H, we don't use H2, we just use H. So 1.008 grams of H. Same here. Normally you use oxygen gas like O2, but since it's just one oxygen, you only use the molar mass of just one oxygen atom. Like so. And for carbon, 12.001, I'm pretty sure. Yeah. So doing that, you get 3.33 moles. Here it's 6.656, but since there's 3 six here, you round this up to 6. For oxygen is 3.33. So looking at these 3 mole values, you divide each of them by the lowest one. So it's either carbon or oxygen. It doesn't really matter which one since they're the same number. So 0.33 moles. 3.33 moles. And 3.33 moles. No, sorry, flip carbon here. But yeah. So you just get 1, 2, and 1. So these numbers are going to be your subscripts for each atom or element, like in the molecule. So the empirical formula is going to be CH2O. Okay, now this is the part where you would normally like have the mass of the molecular formula to find like your whole number multiple of n. But since we're not given that, we gotta work our way around that restriction. So in order to do that, we take the volume of sodium hydroxide, 50.0 milliliters, and let's convert that into a number of moles of sodium hydroxide using the molarity. So let's stay at milli for the prefix. So since we stay at milli, we we convert the moles from moles over liters to millimoles over milliliters. Make sense? So instead of like normally having moles here, it'd be millimoles now of NaOH. And instead of liters being here, it'd be 1 milliliter. So we can do this because we scale everything down equally. If the stuff here was just moles instead of millimoles, then we wouldn't be able to do that. But since we scaled it down to millimoles to match the prefix here for milli, we can do that. So doing that, we get 2 millimoles of NaOH. Okay, so now if you look at the problem, we're given 1 millimole of the unknown acid. So, so if we divide the millimoles of NaOH we just got by the millimoles of the acid, we can get a whole number multiple of N, which is just 2. So this is our N. This is what we'll multiply each of these subscripts by to get the molecular formula. So it's just CH2O, basically times 2, times 2, times 2. And that should give us the correct molecular formula. So it's C2H6O2. That's the acid right there. And this is the molecular formula of the acid. Like I said. So when you're not given the whole number multiple or like a mass you can use to find it, you kind of gotta work your way around that and work with what you have. So you see here, we're given milliliters and the molarity of the base. We can use that to find a whole number multiple using the millimoles of acid given to us. And yeah, that should be it for this one. Okay, so number 19 says, draw the calculus structure for the following formula as well as its 2 geometric isomers. Okay, so let's start off by drawing the formula as a calculus structure. So you see there's like 1, 2, 3, 4, 5, 6 carbon backbone. It's the longest. So we draw 2, 3, 4, 5, 6. And there's one sticking out right there. And one sticking out right there. And there's a double bond right here. If you're confused, let me show you like how I got this. So I'll write out the structure as a Lewis dot structure. So CH2 CH, and there's a C right here with right there. So this is kind of like a rough like idea of how the structure looks like. So here the CH3, C2, CH, double bond, then C where everything branches out. So this top part is this methyl branch. Okay, and this little fork right here is right here. Schultz told me this is an isopropyl group, so I'll just take his word on that. Here's the double bond right here. And here is the methyl or the ethyl branch. This whole thing. So with that being said, this is the correct calculus structure. Now for its 2 geometric isomers, we already have one. And it's this one right here. So isomers are just ways of drawing it differently, basically. So what we want to focus on here is where the double bond is. And is this group right here on the same side of it or against it? So right here, this group is facing this way, but this one's facing down. So this is the cis isomer, or I mean trans isomer, since it's opposite the side the double bond is at. And if we just rotate it, like, sorry, wrong one. So if we draw this isopropanol group, or I mean propanol group, on the same side as the double bond, it looks like this: 2, 3, 4, 5, 6, right here, like this. So this methyl branch is facing the other way now, and the propanol is on the same side now as the double bond. So this is the cis isomer, and this should be it for this problem. So when it asks for isomers or constitutional isomers, you want to think about like where you could rotate, like the prevalent groups, like this right here. Ultimately, you want to revolve around where stuff is like quote unquote interesting. Like, see, you won't like rotate it around here, would you? Because there's nothing here. You rotate it around where the double bond is at. So, like around this point, not this point. Yeah. Okay, last question. Number 20 says, explain the photoelectric effect. So, you guys remember this from exam 3 or 4? I think it's 3. But basically, when light hits an object, like a sheet of metal, for example, it knocks electrons loose and they exit at a specific speed. Okay, but the light, but not all metals are the same. Let's say you're working with like, I don't know, like iron or something. So what if iron like required less energy to break off an electron than like gold or something like that? Then you would have it like this. So the x-axis is energy, and that shows that not all metals are the same, but the electrons exit at the same like angle basically. So, but what if you like what if the beam of light has more energy than usual, right? Well, the energy required for iron to shoot off an electron is the same, but where does the rest of the energy go? Well, it goes into the kinetic energy of the electron right here. So this electron could go faster than the one shot off by gold, maybe. I'm not sure. I'm just making these metals up, to be honest. But yeah. So what you should know is that some metals require more energy to break off an electron than others, but the slope is the same. The only way, the only thing that changes between the electrons shot off is their kinetic energy, basically. Scratch that. This isn't energy. This is frequency. So just, I think it's like V. And the y-axis is kinetic energy. So the excess energy goes into making the electrons shut off faster. So the final is basically just like a Frankenstein of questions from the past, from past exams and quizzes. Um, um, since it's cumulative, you know. But there's also some new stuff like the OChem and boiling stuff, or and boiling point stuff, like I covered in the study guide as well. So, so if you want more, like, if you want more practice on stuff I covered in the study guide, then you should look at your your previous exams for more questions, like the condensed electron configurations, um, like balancing chemical reactions, Let's see, like working with molecular orbitals, like what type of bonds there are, like sigma or pi, doing like the subshell stuff, like the n equals like blank, l equals blank, and ml equals blank, and so on. So just look at your past exams, if you have them. But if you don't, you can always email me for a key if you want it. Oh, just no emails about the final key though, because I can't give you guys that. That should be it for this study guide though. If you guys have any questions, just let me know in the comments. If you have any feedback, just let me know. And yeah, I hope you guys have a good weekend. Happy studying, I guess. All right, see you guys.